True or false, a direction field is just a vector field with equal length vectors. True. Okay, what kind of thing is the notation P with an arrow over it or bold P? A vector.
Did I say equation?
As long as you have the word vector.
I said vector equation.
All right, fine.
Chief,
I mean, it's not an equation because there's no equal signs. I'll give it.
Yeah, right. Okay, everyone get a 4.
Okay, so let's start with some notation. So most of you are in linear, so a lot of this notation is not going to feel crazy new. But we're going to be using some linear algebra vector notation here. Okay, so this is the same predator-prey example that we talked about last class. R prime equals 2r minus 1.2rf, and f prime is negative f plus 1rf. All right, so we're going to use some vector notation to express this system. Remember that vectors are just denoted as bold, or they have a little arrow above them. I'll typically use bold because when you're typing, that's easier than putting a little arrow, but when you're writing on paper, I usually use a little arrow because that's easier. So either one can be a vector. All right, so P of t, P stands for population, right? And it's going to be a vector, and it's going to have 2 entries in the vector, one for rabbits, one for foxes. So P of t is going to be a vector, R of t, F of t. And vectors can be written vertically or horizontally. R of t, F of t, or R of t, comma, F of t. They mean the same thing. They both just mean rabbits, foxes. And when you only have 2 entries, you can think of them as a point, whether it's in the plane, whether it's written vertically or horizontally. So then we can define another vector, P prime, where the derivative of P is just the derivative of each entry. Okay, so R prime F prime is 2r minus 1.2rf and negative f plus 0.9rf, right? Because that was my original system here. I was given R prime and F prime. So this is my differential equations. That's my system of differential equations. This is my solution. Right? P of t is the solution. It's 2 functions, R of t and F of t. So for each vector or point, R comma F in the RF plane, which we call the phase plane, we can calculate P prime. We can calculate a derivative that defines a vector. Since the vector is the derivative of P, the solution, derivatives are just tangents to solution curves, right? So the vectors that we get by calculating R prime F prime are tangents to the solution curve P. And when we plot a bunch of these vectors in the RF plane, we create what's called a vector field. And they show what the solution, how the solution is moving through the vector field, through the phase plane. All right, so we're going to calculate a few vectors in the vector field. So let's do, for any particular RF, right, we can calculate a vector, R prime, F prime. So RF is a location. This is the RF plane. So we pick a point in the RF plane and we calculate R prime, F prime, a vector. All right, so let's try 0, 0. What if I choose 0, 0 as the point in my RF plane?
You get 0, 0.
You get 0, 0 using my formula, right, for R prime, F prime. So if I put in 0 for R and 0 for F, I get 0, 0. So what is a vector? It's just a dot, yeah. So at the point 0, 0, I just have a dot. All right. How about if I do the point 1, 1, 1? So in my derivative formula, right, R prime, F prime, I'm going to plug in 1 for R and 1 for F. So I have 2 times 1 minus 1.2 times 1 times 1. I get 0.8 for R, yeah. And then if I plug in 1, 1 into the second equation, I get negative 1 plus 0.9 times 1, and that comes out to negative 0.1. So at the point 1, 1 in my phase plane, I'm going to draw a vector, 0.8 in the r direction, negative 0.1 in the f direction. So I go almost 1 in the r direction, teeny little bit in the downwards direction for f, something like that. That did not come out right. So hard to be super accurate, but it's good enough. All right, and then how about one more point? What if I pick like 3, 4? All right, I'm going to plug r is 3 and f is 4 into my r prime, f prime equations. And I get negative 8.4, 6.8. Okay, good. So at the point 3, 4 in the RF plane, I can draw a tangent that my solution is, I can draw a vector that my solution is tangent to. So negative 8.4 in the r direction, 6.8 in the f direction is like pretty steep and large. I don't know, something like, it's off the charts, yeah, something like that. Okay, this is super tedious, right? You have to do this for a lot of points in the RF plane in order to get a picture of what the solution is looking like. It's just the kind of job a computer would be good at. So your T89 can do this, if you have one. So can some awesome free software called WinPlot. There's a link there, and I'm actually going to have you use WinPlot or another software in your final project. So if you want to start playing around with it now, you can. But when we get to the final project, there'll be detailed instructions on how to do it. So.
What about Mathematica? Could we use that possibly?
I'm sure Mathematica can do it, yes. I don't know how off the top of my head, so Mathematica can definitely do it. All right, so here are some vectors for the predator-prey system plotted in the RF plane. So I did a whole bunch of them here, right? We also did 1, 1, right? We did 1, 1, and it looked something like that. So it kind of fits in with the pattern of what's going on there. So the arrows tell us about the direction of the solution curve. The length of the arrows tells us how fast the solution curve is being drawn, right? Because remember, time is not in this picture. R and F are the only variables you can really see. But time happens in how you draw the solution, how fast it gets drawn. So the length of the arrow indicates how fast. So imagine driving a car in a big parking lot that's marked with arrows of varying lengths. And you have to follow the solution indicated by the arrows, and you have to speed up and slow down as the arrows get longer and shorter. But having arrows that are all different lengths can get really messy really fast, right? Because they start crossing over each other, and it's hard to see what's happening. So typically, we usually just scale them all to a uniform size. We do lose some information about time, about speed, but usually the resulting graph is so much easier to read that we're okay with the loss of information. And the result is called a direction field as opposed to a vector field because it only tells us about direction and not about speed.
That's all they care about, isn't it?
Yeah. So here's a direction field for the predator-prey model that we've been working with. So you can see the direction field indicates that solutions are spiraling, which is exactly what you found in the activities last class, right? As the rabbit population increases, the fox population increases, but then if the fox population gets too big, the rabbits start to die, and then as the rabbits die, the foxes die, and it just keeps cycling back around.
I have a question.
Yeah.
So one of the questions for the homework, showed a graph, and it was actually spiraling towards the equilibrium.
Sure, yeah.
That indicates that the population is going to die out no matter what, right?
Well, it depends on where the equilibrium point is.
That one, it just went towards that
3,
equilibrium point in the center.
Right, like 1, 3 or whatever. Then they're not going extinct. They're just They're just going to live in balance, so that they will cycle around towards this 1,000 rabbits, 3,000 foxes, and then it will never change again after that.
It kind of oscillates to a nice.
Yeah, it oscillates around towards it.
To a nice balance.
The only time they go extinct is if they both end up at 0, right? If they go extinct. All right, so now it seems possible that we could plot specific solution curves just by following the vector field. So this is almost exactly what we did by using Euler's method, right? Except it's sort of more graphical than numerical. So remember, if you plot several solution curves and the equilibrium points, that's what makes a phase portrait. So if you're asked to draw a phase portrait, that's what you need. Equilibrium points and several solution curves. So that's what I've done on the right here. I plotted the 2 equilibrium points, 0, 0, and this was like 1,5 I can't remember if that's what it was. Yeah. And then you have several other solution curves that oscillate around that equilibrium point. And then there's a couple of others too. Because anytime you start on an axis, like here, if there are rabbits but no foxes, what do you think happens to the rabbits? They're just going to grow, yeah. So those just go for forever getting larger.
Right.
What happens if there are foxes but no rabbits?
They're just gonna go to 0.
They just go to 0 because they have nothing to eat. So there's different kinds of solutions on the axes too.
I thought that our model also included, loss due to old age or whatever. So I mean,
It does not. Because the only thing we took into account in that particular model
Yeah, but I think
was the Malthusian model, in that the population grows in proportion to its size, and interaction between the two species.
if one driver makes it pretty good.
Okay, so sometimes a vector field can suggest where equilibrium points can lie. Like if you look at this picture on the left, you can clearly see there's a point that's being circled here, and you can kind of guess where the equilibrium point is, right? But don't forget, you can always find them explicitly just by setting your 2 equations equal to 0, r prime and f prime equal to 0, and solving. So just a little note here. Now that we're working with systems and have 2 dependent variables like rabbits and foxes, you can see why we've always been using t as our independent variable all semester. You might not have noticed it, but instead of writing differential equations like dy dx and then having stuff with x's and y's, I always use dy dt. And that's because now we can use x and y as our dependent variables, and time will always be our independent variable.
So it's parametric plots pretty much.
Yeah. Yep. All right. That's it. You can start your activities.